Hello everyone, in this video we will discuss Hall effect in semiconductors. So, this Hall effect was first developed by Edwin Hall in the year 1879. So, according to this, when a magnetic field is applied to a current carrying conductor in a direction perpendicular to that of the flow of the current, then a potential difference or a transverse electric field is created across this conductor, and this phenomena is known as Hall effect. And the potential difference that is created is known as Hall voltage, and the electric field due to this is known as Hall field. So, whatever I just said is clearly depicted in this diagram. So, the direction of current is towards x axis. So, my convention of direction is like this: x axis, z axis, and this one is your y axis. So, when your current is flowing in x direction and the magnetic field is perpendicular, which is flowing in the z direction, then there is a potential, there will be a potential difference across this semiconductor, and this force due to this potential difference will be perpendicular to the direction of both current as well as magnetic field. So, what are the applications of this Hall effect in semiconductors? So, Hall effect can be used to find out whether a semiconductor is of n type or p type. It can also be used to find out the majority charge carrier concentration. Apart from these two applications, Hall effect is also used to find out the mobility of the majority charge carriers. So, here we will need a concept of Fleming's left hand rule to understand the first application. So, according to Fleming's left hand rule, when a current carrying conductor is placed in a magnetic field, then it exerts a force. So, according to Fleming's left hand rule, if your middle finger represents the direction of flow of current and the direction of magnetic field is represented by the index finger, then the force exerted is represented by the direction of your thumb. So, using this concept we will understand rest of the things. So, that amount of that force will be equals to I dl cross B. Okay. So, this is your Lorentz force. So, suppose a block of semiconductor is given to you, to which we will apply an external voltage supply V in x direction across its length. So, suppose this is your externally supplied voltage, as it is in x direction, it is represented by Vx. The length of this semiconductor is given by L, the width is W, and the depth being D, and the direction conventions are: this is x direction, this is z direction, and this is y direction. We will follow this concept of direction throughout my lecture. So, semiconductor, a magnetic field is applied which is perpendicular to the flow of current. So, here in this case the current's direction will be in this direction, in x direction. Okay. So, a magnetic field is applied, or this current carrying semiconductor is placed in a magnetic field which is in z direction. Okay. So, a force will be experienced which will be perpendicular to both I and B. Okay. So, according to Fleming's left hand rule, if your current direction is shown by your middle finger and the direction of the magnetic field is shown by the index finger, then the direction of force will be shown by your thumb. So, here according to Fleming's left hand rule, the force will be experienced in this direction, that means in y direction. Okay. So, suppose this is a p type semiconductor. So, in case of p type semiconductor, the majority charge carriers are holes. So, due to this voltage Vx, what will be the direction of flow of holes. So, it will be from positive to negative side. So, the direction of holes will be from left to right or from positive to negative terminal of this voltage supply. So, what will be the direction of current? So, the direction of current is same as the direction of flow of hole. So, if I am considering current, so its direction will also be same as that of the holes. Okay. So, now due to this force, what will happen? These holes will move towards this side. Okay. So, holes will come to this side of this semiconductor block. Okay. And so, positive charge will be accumulated over here. So, as the holes have moved here, so here there will be positive charges, and accordingly electron will move to the back surface or to the surface at the back. So, due to this kind of distribution of electrons and holes, so there will be a potential difference generated across this width of this semiconductor, and that can be measured by connecting a voltmeter across these surfaces. So, here I am connecting a voltmeter here to this surface and this surface. As I have already mentioned, the voltage or the potential difference developed here is known as Hall voltage, and suppose the positive terminal is connected to the front side and the negative terminal is connected to the back side. So, here as the positive terminal is connected to the side where holes are present and the negative terminal is connected to the side where electrons are present. So, the voltage, the Hall voltage will be positive. So, here the Hall voltage will be positive. Okay. So, P type semiconductor, the Hall voltage will be positive. Similarly, for a N type semiconductor, the Hall voltage that is generated will be negative. Now, let us see. So, suppose this is this is a block of N type semiconductor. Again, here we have connected the voltage supply Vx, due to which the current is moving in the x direction, and this is placed in a magnetic field which is directed towards the z direction. So, what will happen? According to Fleming's left hand rule, the force will be exerted towards this surface or towards u. So, here the force will be in this direction. Again, for N type semiconductor, the majority charge carriers are electrons. So, here electrons will move in which direction? So, electrons will move from the negative terminal to the positive terminal, that means from right to left. So, the direction of current, as I have said earlier, will be in this direction. So, this is the direction of current. So, now as I have said, there will be a force in this direction. So, what will happen? This will affect the movement of electron. So, the electrons will be drifted towards this front side. So, the electrons will be accumulated over here, and similarly holes will be accumulated in the opposite side. So, there will be a potential difference generated across this semiconductor, and this can be measured in the similar fashion, that means by connecting a voltmeter across this. So, see here the terminals of this voltmeter, and to the side it is connected, and the charges accumulated in this side. So, here the sign of this Hall voltage will be negative. So, we can say that for an N type semiconductor, the Hall voltage developed will be negative. So, here the first application is explained, That means for a n-type semiconductor the Hall voltage is negative, and for a p-type semiconductor Hall voltage is positive. So, given a semiconductor, you do not know what type of semiconductor it is, then you can determine its type by finding out the sign of the Hall voltage. So, if it is negative, then you can say it is an n-type semiconductor, and if it is positive, you can say it is an p-type semiconductor. Now, I will explain the second application, that means we can find out the majority charge carrier concentration. Okay. So, for this we will need the equation of force. So, what is the force due to magnetic field? So, it is Q V cross B, where V is your velocity and B is your magnetic field. Similarly, force due to electric field is equals to Q into E, where E is equals to your electric field. Now, at equilibrium, this magnetic field is equals to the electric field. So, according to Fleming's left hand rule in the previous figures, so what was the direction of this force? So, it was in y direction, and the direction of magnetic field was in z direction, and the electrons, or we can say the this velocity is consider again a p type semiconductor here. Okay. So, this direction of this velocity will also be in x direction. So, we can write down V x cross B z. Okay. So, this is a cross product. So, we can write down this as q V x into B z into sin theta. So, what is the angle between this velocity and the magnetic field? It is 90 degree, and the value of sin 90 is 1. So, we can simply write down this as q into V x into B z. Similarly, this force due to electric field is equals to F y, and it is q, and the direction of this electric field is in which direction? The electric field due to the potential difference of due to Hall effect. So, that is in y direction, right. So, this is equals to E y. Okay. So, at equilibrium, this q into E y will be equals to q into V x cross B z. Okay. So, now this equation can be rewritten as, so q from both sides will get cancelled, and we can write down it as E y is equals to V x into B z. Now, what is the electric field? So, electric field, it is the ratio of voltage to the distance. So, here voltage means Hall voltage. So, what was the Hall voltage? VH, and it was, if you remember the diagram that I have drawn, so it was developed across the width of the semiconductor. Okay. So, as I have considered this as a p type semiconductor, so here there will be holes and there will be electrons, okay, given a external voltage supply Vx. Okay. So, potential difference is generated across the width of the semiconductor. So, in place of this distance we can write down W. Okay. Now, let us replace this E y in this equation. So, it will be V h by W is equals to V x into V z. Okay. So, what is the value of this velocity? So, this will be equals to V h divided by W into B z. Now, consider this as equation 1. Now, what is this velocity? So, this velocity is generated due to the externally applied voltage supply, isn't it? So, we can say this as the drift velocity. Now we remember the expression for drift current density. So what is drift current density? So this is J. So the current is moving in x direction, so it will be Jx. So the drift current density is equals to E, and it is a p type semiconductor. Okay. So E into concentration of holes into mobility of holes, that is mu p, into the electric field due to this voltage. So that electric field is towards x direction. Okay. And what is drift velocity? Drift velocity Vx is equals to the product of mobility into the electric field. Now replace this relation over this equation. So Jx is equals to E into P into Vx. So what will be, and what is Jx? This is the current density, that means current per unit cross sectional area. That is equals to E into P into Vx. So what is the cross sectional area? As the current is moving in this direction, so the cross sectional area will be the product of W into D. So I am replacing the value of area here. So it is W into D is equals to E into P into Vx. So what will be the expression of Vx, that means the drift velocity? So it is equals to I divided by W, that means Ix divided by W D into E into P. So this is the expression of drift velocity. So consider this as equation 2. Now we will equate this equation 1 and equation 2, because both these equations are equation of drift velocities. Now let us equate. So it will be equals to equating 1 and 2. We can write down it as Ix divided by W D into EP is equals to Vh divided by W into Bz. Okay. So W from both sides will get cancelled. Now we are interested in finding out the concentration of majority charge carrier. So here the concentration is P. So P will be equals to Ix into Bz divided by D into E into the Hall voltage, that is Vh. So in this expression, Bz is the magnetic field applied, the value is known. D is the height or depth of the semiconductor block. So it can be obtained from the dimension, given dimension. E is 1.6 into 10 to the power minus 19, and Vh is the Hall voltage. So it is the reading of the voltmeter. Now Ix, it can be measured by connecting an ammeter. Okay. So where the ammeter should be connected? So you should connect the ammeter over here. So if you connect the ammeter over here, so it will give you the value of the current Ix. Okay. So by obtaining those values, we can find out the concentration of the holes for a p type semiconductor. Similarly, for an n type semiconductor, the expression of the expression for the concentration of electrons is given by minus Ix into Bz divided by D into E into Vh. So here I have considered negative sign just to neutralize the negative sign of the Hall voltage. Okay. So this is the concentration of electrons in case of n type semiconductor. So with this I have explained the second application of Hall effect. Now we will come to the third application. So what is the third application? So the third application says that we can find out the mobility of majority charge carriers. Now considering the same thing, so first I am taking a p type semiconductor. So for a p type semiconductor, we have seen that the current density is equals to E into P into mu P into Ex. This expression we have just seen. So, here for this current density I can write down it is Ix divided by W into D. And what is this Ex? So, this is the electric field generated due to the voltage supply Vx, okay, and this voltage is applied across the length, if you remember. So, this voltage is applied here, that means across the length. So, here distance will be L, okay. So, Ex is equals to Vx by L. So, let us replace this value of Ex in this equation. So, Ep is equals to mu P into Vx divided by L. So, now I am interested to find out the expression for the mobility of the majority charge carrier. So, here it is mu P, which will be equals to Ix into L divided by W into D into E into P into Vx, okay. So, see, everything is known to you. L, W, D, these are the dimension of the semiconductor block supplied. E is equals to 1.6 into 10 power minus 19, P is the concentration of holes, Vx is the voltage supplied, and Ix is the current, okay. So, all these things are known. So, from there you can calculate the concentration of the mobility of holes. So, similarly for n-type semiconductor you can find out the expression of mobility as Ix into L divided by W dE into N into Vx. So, this is the expression of mobility of electrons in n-type semiconductor. Now, I will discuss about the Hall coefficient. So, the Hall coefficient is given by RH, that is equals to P into mu P square minus N into mu N square divided by E into P mu P plus N mu N whole square, fine. So, this is the general expression for Hall coefficient. The derivation for the derivation of the Hall coefficient I will post another video. So, for the time being, here we will discuss what will be the Hall coefficient for p type, n type semiconductors. So, here let us consider a p type semiconductor. So, for a p type semiconductor, the concentration of holes is much greater than the concentration of electrons. So, I can say P into mu P is much greater than N into mu N. So, I can ignore the term N into mu N from both numerator as well as denominator. So, what will be the expression of Hall coefficient? So, it will be equals to P into mu P square divided by E into P mu P whole square. So, the terms common from the numerator and denominator will get cancelled. Now, we will be having RH equals to 1 by E into P. So, this is the Hall coefficient for p type semiconductor. So, this is a positive quantity. Similarly, for a n type semiconductor, I can say N into mu N is much greater than P into mu P. So, I can find out the expression of RH for n type semiconductor by neglecting P mu P from both numerator and denominator. So, if you put the value, you will get the expression of RH is equals to minus 1 by E into N. So, N is your concentration of electrons. So, it is negative. Now, so this is for extrinsic semiconductor. Now, let us see what is the Hall coefficient for intrinsic semiconductor. So, for an intrinsic semiconductor, the number of electrons is equals to number of holes, that is equals to Ni. So, let us find out what will be RH. So, it will be equals to Ni into mu P square minus mu N square divided by E into, I can take out Ni square outside because it is a common term, and it will be mu P plus mu N whole square. So the term in the numerator will be equals to mu p plus mu n into mu p minus mu n divided by mu p plus mu n whole square into E into Ni square. So this term will get cancelled from both numerator and denominator. Now RH will be equals to Ni. Ni again will be cancelled from the numerator as well as from the denominator. So the expression will be equals to mu p minus mu n divided by E into Ni into mu p plus mu n. So this is the expression of Hall coefficient in case of intrinsic semiconductor, but ideally this RH is equals to 0 for an intrinsic semiconductor. But generally this is for ideal case. But generally what happens, suppose for silicon mu n is greater than mu p. So for general case, as mu n is greater than mu p, RH is negative for a intrinsic semiconductor. So with this I have come to the end of this lecture. So if you have any doubt, you can post it in the comment section. Thank you.